Let's implement a least recently used cache in under 5 minutes. This is one of my favorite data structures and algorithm questions. It's a proper LeetCode medium because it touches on so many potential different implementations. And if you haven't seen this question before, the final optimal solution might surprise you. It uses a unique data structure. Stay to the end. The least recently used cache is a key value pair cache with a special eviction rule, such that the least recently used item put into the cache is the one evicted when we reach our capacity. Think of this as a carton of eggs. Take that dozen of eggs, and then let's think about just one row. So you have 6 eggs, and now you want to put one more egg into this 6-egg carton, and you need to figure out what is the oldest, nastiest egg that you want to throw out to replace it with the newest, coolest, freshest egg. So you have these fresh eggs. That's one way that you can think about an LRU cache. We want to evict the old one, so we want a cache, but it's an interestingly ordered cache used to maintain freshness. With an ordinary cache, we'll be thinking of a dictionary or a hash map, but now that we know that we want order, we should be calling to mind an array-like structure. In fact, maybe an array literal, because an array literal has the interesting property that it can operate as a hash table as long as the key is an integer, and it can maintain order. So we're thinking through potential data structures that would be appropriate here. We're thinking of a dictionary, we're thinking of an array, but there are some other array-like structures, perhaps a linked list. Then there are some special built-in structures to certain languages, like the ordered dictionary in Python. But let's ignore that for now because those higher order structures will use the lower order implementation that we'll arrive at under the hood, and the lower order implementation that we're going to arrive at is language agnostic. So let's not depend on those built-in modules. So let's consider the dictionary. The dictionary by itself won't work simply because we can't preserve order. We might use a dictionary in combination with something else, but we won't use it alone. So for now, let's move on. Now let's consider the array. So with the array, I can append to the array an O of 1. We want to take note of this instruction. The functions get and put must each run an O of 1 average time complexity. This is a crucial hint, actually. So we can append to the array, and then we will be having the least recently used item early in the array. It will be like the 0 index. We'll keep appending, and then we can evict with pop 0. We can just take that first one off. So we can remove an O of 1 time. That's good. But here's the problem. Every time that we get an item, it will effectively refresh the order of use of that item. So if I have a key value pair where the key is 2, and then I update the value, so the original key value pair is 2 and 6, the new key value pair is 2 and 7, that causes the location of the 2 to become freshly used. So it will move to the right, it will move to the end of the array. So because we need to do that refresh operation, actually the array becomes a lot less attractive because whenever I want to move one of these eggs or nodes, it will move it, and that will cause me to look through the array, find it. I can potentially find it in O of 1 if I know the key, right? But now that I need to move the location, that is going to cost me O of n. That is the expensive operation that's a constraint here, and it's going to rule out our ability to use a vanilla array. Now you might think if I have a dynamic array in the index, can't I pop out of the index or split it into 3 subarrays, move the relevant item to the end, and then join in constant time? And the answer is no. That operation looks constant time, but under the hood, the stitching is O of n because Python will actually create a new dynamic array. It's actually easier to envision this if you think about it using a static array, where you might pop out an element and replace it with a null node, move that element to the end, and then you need to slide down every element. That's more like what's actually going on from a time complexity perspective. So what about our other array-like structures? Well, we can use the linked list. Now that comes in single and doubly linked flavors. And the doubly linked flavor will be necessary for us, and it's due to that same popping. When I pop out of the middle of the array, I want to avoid an O of n operation. The doubly linked list, when I pop the element out or this node out, I have the knowledge of the left and right neighbor, so I can stitch together those two subsections, those two sublists. I can do that in constant time because I have left and right data on which nodes to stitch. In the context of a singly linked list, this would cost me O of n because I'd have to navigate through to find the old left neighbor who is pointing next to the current one that I'm popping out. So in the singly linked list approach, my current node knows next, but he doesn't know previous. So I know the right neighbor, but I would need to navigate the front of the array to find the old one who has to restitch the new next. Does that make sense? So that's why the doubly linked list is actually the optimal solution in this situation? The doubly linked list with a dictionary. So how can we do the get or the pop or the update in O of 1? Because we have a dictionary which is pointing to these nodes. And so if I want to make an update on the node, I can do that in O of 1. I can get a reference to the node in O of 1, but then I can do the movement with a head reference, with a tail reference, and then the stitching. I can do those in O of 1 on the linked list entity. So the combination of these two data structures, a doubly linked list and a dictionary, or a hash map would be the generic term. In Python, this specific term would be a dictionary. This is your object in JavaScript, plain old object. That turns out to be the optimal combination of data structures and algorithms for the LRU cache. So I hope you found this interesting. I really like this problem because it causes us to think through so many different data structures and algorithms all in one actually practical problem. This is like a real tool that we really use. And you know, with LeetCode, there's a whole bunch of problems that touch on stuff that we never deal with. But the concept of refreshing and keeping a fresh cache is actually like super, super relevant in programming. Hope you found this interesting. Follow for more.